All right, let's take a look at this question. It's saying the first and the second ionization enthalpy. Okay, so the delta H1 and delta H2.2, first and second ionization enthalpy, okay, in kilojoule per mole. And the delta Eg electron gain enthalpy in kilojoule per mole of a few elements are given below. Where below? Nothing is given below. Nothing is there. Where is everything? Here is everything. Okay, so we have this list over here. What do we have? We have P, and in P, as you can see, what do we have here? In P, we have 2520, then we have 7300. You see, right? 2520, 7300 minus 60, right? This is what we have. We have 4190. Oh, shoot up 3051. And okay, so in the top one we had 2520, then something that was like 7300. So that was about approximately 2.8 or 3 times the value. But here, if you take a look, right, from 400 something we are going to 3000 something. That's more than a 6 times jump, right? And it doesn't want to accept electron, neither this, neither. Okay, so no, delta H is release of energy, but not as much. Okay, fine. So it will accept electron, but not that much stability will be gained by it, right? Okay, cool. So what I think is that in this case here, what we are dealing with is actually something that is a group 1 element, if you ask me, because it loses the first electron quite easily. Then the second electron, the noble gas electron, turns out to be quite difficult, and still gains the electron because it wants to go from S1 configuration to S2 configuration. Certain stability is gained, but that is not as much. It would rather lose electron. Okay, this one over here, I'm not pretty sure because the values itself do not convey much. But yeah, from going from 2520 to 7300, that's not much of a jump, right? That's not much of a jump, right? Okay, cool. But still, that's not quite reactive if you ask me. Group 1 is any day superiorly reactive. Then in the third one, what is happening is we have a decent first ionization energy. Our second ionization energy is proportionate, right? Okay, there's no sudden jump like the second case. And then a lot of energy is released when it accepts an electron. Okay, so what would we say this could be? So it accepts electron, releases a significant amount of energy. Okay, it loses an electron, so maybe it is P2. It becomes P1, and then P1 S2. No, P1 S2 should actually be relatively stable. How about this is P5 becomes P4, P4 becomes P3. No, that is also not sorted here, right? Okay, maybe it is P4. So P4 to P3, okay, some energy is required, and P3 to P2, a much larger energy is required, and it gains an energy. So yeah, this could be a group 16 elements somewhere in the oxygen family. Could be. I'm not really sure, but definitely reactivity wise, if I have to say, still the group 1 element, that is Q here, tops the list, right? When we talk about S here, we have 1008, we have 1846, and we have this. Okay, so it requires less energy than that to lose an electron, the first one. The second one requires less than double. Okay, and then a significant release of energy when it gains an electron, right? Okay, so what could it be? What could it be? So remove 1 electron, remove 2 electron, I'm fine either way. But second time you're removing from a positive charge, so any which way the energy is larger. This could be, probably this could be, a group 14 element, right? P2 configuration loses 1 electron, P1, then P1 loses another electron. So not as much energy required, but still you're removing from positive charge. But when you give an electron from P2, it becomes P3, and that's quite stable, so it releases a lot of energy, right? Okay. If I look at this one, tons of energy required, then again, and does not want to gain any electrons. Okay. Okay, so how about this one? What shall we say about this one? This looks something that belongs to maybe, this definitely is in group 2. This definitely is in group 2. This could be group 13, however, right? Could be group 13, but I wouldn't be too sure. But any which way, the most reactive, which the question asked in the beginning, so far, this is not going to be a very, very reactive element, at least if we compare it with Q, right? And if we compare it over here, we have one electron removal, second electron removal, some energy is released. Then again, right, it's bit of a vague. We cannot really, with 100% confidence, classify this within a particular group. But yeah, we can say that this still isn't as reactive as our group 1 element, that is Q over there. Let's look at the options. Oh yes, Q is there, and with that, Q is going to be my response, the correct response in my opinion for this particular question. All right, let's take a look at this question. What is it trying to say? It's saying two weak bases AOH and BOH have equal concentration of 0.5 molar. They are present in the solution. Okay. Calculate the ratio A plus by B plus at equilibrium. Dissociation constant for AOH and BOH are also provided. All right. So let's consider this. We have AOH. It dissociates as A plus and OH minus. Similarly, we have BOH and that dissociates as B plus and OH minus, right? Okay. Let's write concentrations over here at equilibrium. This will look like something like this and something like this, right? Okay. At equilibrium, this will look something like this. C2 alpha 2 over here, C2 alpha 2 over here. But we have to consider the common ion effect, and we have to accommodate a C2 alpha 2 over here in the top one and a C1 alpha 1 in the bottom one here, right? Okay. If I write the expression of, KB1 and KB2 here, right, KB1 for, let's say, AOH and KB2 for, let's say, BOH, those expression I'm going to divide as well, right? And you'll understand why I'm trying to say that, right? That will turn out to be C1 alpha 1 plus C2 alpha 2 multiplied by C1 alpha 1 divided by C1 1 minus alpha 1, right? Okay. And the other one will be C1 alpha 1 plus C2 alpha 2 multiplied by C2 alpha 2 divided by C2 1 minus alpha 2, right? This is what we have. Now, another thing is that, the concentration is 0.5 molar, which is pretty decent. And the values of KB1 and KB2 are pretty small. So, yeah, I can approximate this over here as 1 only. 1 minus alpha 1 can be approximated as 1. 1 minus alpha 2 can also be approximated as 1, right? Okay. Another thing is, look what you are looking at, right? What you see here, essentially, if you think about it, right, what you see here essentially is that, let's come back, right? Let's come back. What do we have to find? We have to find A plus by B plus ratio, right? So think about it. What is A plus by B plus ratio? What is this value, right? In terms of C and alpha only, think about it. This is C1 alpha 1 divided by C2 alpha 2. This is what we have, right? So what I'll do is I'll take this C1, I'll bring it to the other side, right? Okay, it will get multiplied over here. So this will get cancelled. I'll do a similar thing with this C2 as well. This will get multiplied over here as well. This will get cancelled out. This will get cancelled out. This here, what we have. So the answer actually is going to be C1 into KB1, which is the KB of AOH, and C2 multiplied by KB2 is the denominator, KB2, which is the KB of BOH. And all that is left right now is basically, to put the values. Further, equal concentrations are there. So C1 and C2 are same. So they can be further cancelled. And it is only a ratio of KB1 and KB2, which is 1.1 into 10 to the power minus 8. 1.1 into 10 to the power minus 8 divided by 1.7 into 10 to the power minus 9. Okay, awesome. Great. Let's sacrifice the decimals. This is what we have here. Let's bring a 10 over here. So we have 110 by 17. Now 17 fives are, if you ask me, that's 85, right? That's 170 by 2. And if we add another 17 to it, basically what do we get here? We get essentially 102, right? Okay. We add another, it becomes 119. So that's beyond 110. What I'm trying to say here is that this value here is coming out to be 6 point something, right? And when I look at it, the option C here is turning out to be something that is quite close to it, right? This is 9 and above, not possible. This is 0 point something, 3 point something, not possible. We are looking at something that is, somewhere between 6 and 7, right? And the value in option C is the only one that is, closest to what our answer is. And the values in option A, B, and D are quite away from it, right? With that, we'll call option C our correct response, and this question can be concluded. All right, let's take a look at this question. It's saying, consider a diprotic acid H2A. Okay. The dissociation constants for H2A and HA minus are this and this. Okay. The pH of this much molar aqueous solution of H2A will be what? Okay, fine. So look, two things are at play here. First, H2A is dissociating into H plus and HA minus. And second, HA minus is further dissociating into H plus and A2 minus. Now, when I look at the values, the first one has 10 to the power minus 6. The second one has 10 to the power minus 13. So I'm going to neglect the dissociation of HA minus. I'm only going to consider it from the perspective of the first dissociation. With that, I can just proceed it like a mono basic acid over here. We have C1 minus alpha, C bracket 1 minus alpha, C alpha, and C alpha. Is there some strong acid present? No, it isn't. And now it's a simple question, right? So it's a simple question. What do we have to do here? We have to, also we can 10 to the power minus 6. So we can further approximate this part as well, right? The concentration value is also pretty nice, right? Okay. So the Ka value, or the Ka1 value, which is 10 to the power minus 6, does turn out to be C alpha square divided by C, right? And C alpha square, which is basically H plus ion concentration square, is turning out to be 0.25 into 10 to the power minus 6. Having done that, what do we get? We can get rid of this part, right? Now we can get rid of this part. Correct? No? Right? Okay. So having done this part, this calculation carries on over here. H plus concentration is equals to the under root of 0.25 multiplied by 10 to the power minus 6. Let's remove this. Let's convert this 10 to the power minus 6 to 10 to the power minus 8. And the under root obviously is there. So the under root, after that, after applying the under root operation, we get 5 multiplied by 10 to the power minus 4. And taking a pH of that, this turns out to be 4 minus logarithm of 5 to the base 10, log to the base 10, which is 4 minus 0.7, which is 3.3. And wow, I'm happy because I see an option matching that exactly. With that, the option A here is indeed the correct response. And from our end, the question is concluded. Alright, let's take a look at this question. This question is saying, calculate the degree of dissociation alpha 1 in a solution obtained by mixing equal volume of 0.02 molar AOH and 0.2 molar BOH. Okay, so note down that this is equal volume, right? So basically what I can say directly is that the C1 new concentration is going to be 0.02 multiplied by volume V divided by 2V. So that's basically 0.01. And the C2 new concentration is actually going to be 0.2 molar multiplied by V divided by 2V. So that's going to be 0.1, right? Okay, cool. We have AOH and BOH. Okay, have we been provided the KB values? Yes, indeed. Alpha 1 is degree of dissociation for AOH. Alpha 2 is for BOH. All right, cool, fine. So now what do we have here? This is a case of weak base 1 combined with weak base 2, right? Okay. And what is going to happen? So let me, just write the expressions here. What is going to happen is that, first of all, the OH minus concentration is going to be C1 alpha 1 plus C2 alpha 2, right? Okay, what else do we have here? The first one is AOH, right? So the A plus concentration is going to be C1 alpha 1. The B plus concentration is going to be C2 alpha 2. The AOH concentration can be approximated. Can it be approximated? Yes, indeed, it can be approximated, right? These values are pretty decent, the C1, C2, and the KB1 and KB2 are quite small. So that can be approximated as C1 and the BOH can be approximated as C2. Why are we saying that? Because, this actually would have been equal to C1 bracket 1 minus alpha 1, but we are ignoring this. So this becomes equals to C1. This would have been C2 bracket 1 minus alpha 2. So we are ignoring this. This becomes C2, right? Okay. Having said that, what do we have to find? We have to find out the value of alpha 1. Okay. Let's proceed on to the next page, right? So, okay, actually, you know what? We can do a lot of stuff here only. How shall we go about it? So, if we can find... Okay, great, awesome. So, look, the OH minus concentration here is actually going to be what? I'm not going through the entire steps of it, but I think you can recognize what I'm going to write here. OH minus concentration square is going to be equals to C1 KB1 plus C2 KB2, right? And we can take an under root on either sides and this is what we get. But why is this important? Because this is equals to what? As we have written over here, right? This is what we have written over here. This is what it is equals to. Okay. And what is this value going to be? Let's see about that. Let's see about that in a bit, right? We'll calculate it. The point what I'm trying to make here is that, if you write the expression for KB1, it's going to be what? OH minus concentration, which is C1 alpha 1 plus C2 alpha 2 multiplied by C1 alpha 1 and divided by C1 1 minus alpha 1, wherein alpha 1 can be neglected. The C1 here can get cancelled out and this is what we have, right? So the answer, that is alpha 1, that is going to be equals to KB1 divided by OH minus concentration, which is equals to KB1 divided by under root C1 KB1 plus C2 KB2. This is what we have, right? We can put in their respective values. So what is KB1 here? 10 to the power minus 8, right? This is what we have. So let's put in this value, 10 to the power minus 8. Let's divide it by the values of, C1 KB1, summation C2 KB2 under root, right? So what do we have over there? We have C1 new as 0.01. We'll put in that value, 0.01 multiplied by 10 to the power minus 8, right? Then what do we have? We have C2 KB2, right? So we have 0.1 here and we have KB2 here as 2 into 10 to the power minus 9, right? So this is what we have. Okay, cool. So we have 0.1. Do we have 0.1? Yes, we do. We have 0.1 only multiplied by 2 into 10 to the power minus 9. All right, so this is what we have. What are we going to do now? Look, this entire thing, right? This entire thing can be concised to 10 to the power minus 10. This entire thing can be concised to 2 into 10 to the power minus 10, right? So this is what we have. It's going to come out as 10 to the power minus 5. I'm doing this calculation here. So alpha 1 turns out to be 10 to the power minus 8 divided by 10 to the power minus 5. And we have an under root 3 in the denominator, right? If I cancel this and this out, this becomes 10 to the power minus 3 and this is what I get. Now I know it's weird, it's a very weird value, 1 divided by 1.732 into 10 to the power minus 3. I agree, right? So 1 by 1.73 is going to be relatively quite difficult to solve. But we can still approximate and see whether that's going to help us or not, right? So we can approximate this as 2, and if we do that, we know that it's going to be 0.5 into 10 to the power minus 3, right? So we can instead write that this is 0.5 something something, because the denominator is actually less than 2, so the actual value will be more than 0.5, right? And we have 10 to the power minus 3 here. We can also call it as 5 point something something into 10 to the power minus 4, right? Okay. Looking at the options over here, I see that, not this, not this, not this, only option B over here is indeed actually very close to the value that we have found as an approximation. And so, still, with confidence, I will select option B for Bangalore over there as my response. Alright, let's take a look at this question. It's saying calculate the number of oxygen molecules required to combine with 7 grams of N2 to form N2O3 when 80% of N2 is converted to N2O3. Okay, cool. So 7 grams of N2 is there. Okay, 7 grams of N2 is there. Right, it's combining with the N2O3 to... Sorry, it's combining with O2 to give you N2O3, and let's balance it out, right? Okay, but only 80% of it is converting into that. So what is the number of molecules of oxygen required for this? Okay, so first of all, what is 80% of this, right? What is 80% of this? So that's 7 multiplied by 0.8, so that tells me that this is 5.6 grams. Oh, that's good, right? That's good, because if that is the case, then we know that the number of N2 reacting, right, reacting is equals to 5.6 divided by 28. So that's basically what, 0.2 by 1, right? So that's 0.2 here, right? Okay. So based on that and applying stoichiometry, number of moles of N2 reacting here, right, divided by 2 should be equals to number of moles of O2 divided by 3 here, correct? And the numerator here is obviously going to be 0.2, and we can cancel that part out and we can get 0.1 here, and we get the value that a number of moles of O2 is equals to 0.3, right? Okay, cool. Now what do we have to answer here? We have to tell the number of oxygen molecules. All right, so we have the number of moles, right? Just multiply Na to it, Avogadro number to it, right? So if I have the number of moles of O2 essentially is equals to 0.3, the number of molecules of O2 becomes number of moles multiplied by the Avogadro number, which is N capital and subscript capital A. And this turns out to be 0.3 multiplied by 6.022 multiplied by 10 to the power 23. And this gives me the value as... Okay, I'll get rid of this 3. This will become 22. Okay, so that gives me 18 point something multiplied by 10 to the power 23. And with that, if I take a look, what do we have over here? Okay, so this is 22, right? Now, if we take a look over here, what do we get? We get essentially what? Okay, so let's convert it into something that looks like the options, right? So what do we have? We have let's multiply and divide this by 10. So this and this I'm combining together. This is 1.8 something. So this is 10 to the power 23. All right. And when we look at that, what do we see? We see that, option B here, which is basically what? Exactly, if not, almost, if not exactly, almost similar to what we have gotten here, which is 1.8 something into 10 to the power 23. And with that, option B for Bangalore here is indeed the correct response.